Okay, so the other day, we were talking about position versus time graphs. Okay, and what we learned from those was that you can tell where the object is at various points in time. From the shape of the graph, you can tell what kind of motion it's undergoing. Okay, if it's a curve, it's accelerating because the change in position isn't uniform. Okay, if it's a diagonal line, then the change in position is uniform and it's traveling at a constant velocity. Okay, and then of course, if it's a horizontal line, then that means it's not moving. Okay, we also learned that you can calculate distance, displacement, average velocity, and average speed, okay, from a position versus time graph. And then if you have a position versus time graph, like what's on your lab, okay, from yesterday, that the slope of that line is showing us the rate at which position changes, okay, or the velocity of the object. All right. Now we're going to look at the other kind of graph that we're going to cover in this unit, and that is velocity versus time graphs. Okay? Now, the one on the left here, this is a position versus time graph. Okay? What is this object doing? I kind of just said it a minute ago. Okay? So position versus time graph, the line's diagonal.
It's moving at a constant rate.
Moving at a constant rate, or at a constant velocity, in this case, in a forward direction. Okay? Could I calculate what that velocity is with this graph? I absolutely could, right? I mean, if I want to use y equals m times x plus b, I could totally do that here. Okay, even though the graph didn't necessarily give it to me, okay, I can still use it because I can say that this is y, okay, that this is b down here, and I have x being 5 seconds, right? So m is going to be y minus b over x, and I'm just going to go 1,400 meters minus 100 meters, okay, divided by 5 seconds. Okay, when I do that, I should get, I think it's 260. I'll fire up the calculator so I don't have to guess too much. Okay, positive 260 meters per second. Okay, that's stuff we learned on Tuesday. What is, oh, I gotta take that line off there. That line shouldn't be there. That's a velocity versus time graph there on the right. What is that object doing? Okay, velocity is on the y-axis, time is on the x-axis. What's happening to that object's velocity? It's the same. Is that object traveling at a constant velocity? Okay, but on that graph it looks different. This is the same object. Okay, we just calculated from this graph that the object was traveling at positive 260 meters per second. Look where the line is on this graph. Just above 250. This is the same object, but the graph looks very different. Okay, this is that same kind of theme that's come up over and over in this unit. It's the same story from different points of view. One is looking at it in terms of the object's position. The other one is looking at it in terms of the object's velocity. Okay, anytime a line is horizontal, it simply means whatever's on the y isn't changing. So that is still an object traveling at a constant velocity. Everybody with me there? Okay. So if both of these are showing an object traveling at a constant velocity, neither one of them is accelerating. True? Because acceleration is a change in velocity. Okay? What's that object doing? What's happening to its velocity? It's increasing. Okay, that means it's changing. Any change in velocity means the object is accelerating. Okay, that's what acceleration looks like on a velocity versus time graph. If I did a position versus time graph of that, it would look like this. right? It would be a curve. The rate of change of position would be changing in a non-uniform way. Okay, so being able to interpret graphs, that's certainly something I'm going to ask you to do. I give you a picture of a graph, you don't even have to calculate anything. What's happening here? Okay, oh, okay, well on this side is y, okay, and this is what you want to do every time. Don't memorize it. Okay, I look at this and I say, okay, I've got velocity, the line's going up, so velocity is increasing over time. Any change in velocity is acceleration. Boom, I'm done. I analyzed it. I didn't have to memorize that the diagonal line on this graph means this. Okay, I want you to learn the method, not the rules. Okay, I don't want you to memorize what every shape on every graph means. You'll eventually get them mixed up. Okay, what I want is for you to go through the method every time. Okay, it's way more reliable to do that. Okay, what if, I'm just going to take this back off of here. Could I calculate what the displacement of the object is on the diagonal line? Do we have a formula for that? Okay, we were using it the other day, right? Displacement equals final position minus initial position. I know I can use that formula because position is on here. Okay, so that formula is valid. Okay, so the final position was 1400. Okay, the initial position is 100. What's my displacement? 1400 minus 100 is 1300. Okay. Could I calculate the displacement off of this graph? Okay, I'm pretty sure there's a way. What is that graph telling me?
Velocity in time.
Velocity in time. Okay, I know that the time is 5 seconds, and I know that the velocity is 260 meters per second. If I've got velocity and time, can I calculate displacement? Just v equals d over t, right? Okay, so multiply both sides by t. Okay, t comes over here. Okay, divide both sides by v. All right. Oh, sorry, I'm supposed to be solving for t. I don't have to do the v part. Okay, so I multiply both sides by t, and I'm there. So t times v, 5 times 260. I mean, it had better come out to the same number. It's the same object. Agreed? Okay. We done anything new yet? Okay. What we're trying to show you here, guys, is that these formulas come from graphs. Thus, they can be used on graphs. They can calculate all kinds of things. Okay. Are you still having to figure out what the graph gives you? Which is the same as pulling givens out of a story question. Okay, that is probably the most important skill you can get for physics, is being able to determine what you have. Because without knowing what you have, you can't get to what the question wants. Okay, so being able to look at a graph and go, okay, I've got velocity. I can see the velocity is not changing. All right, I can go from there. I've got a position versus time graph. The position is changing. I can read initial position, final position, and time. Write down your givens. Where can I go from here? Okay, as long as you follow those steps. And for some of you, it might seem tedious. Okay, it might seem really tedious to do that on every question. Okay, but it's important that you do it. Okay, because I see when people don't do all the little steps that seem tedious, and they make silly mistakes that they shouldn't make because they're smarter than the mistake they make. But they make a mistake because they're not organized enough. Okay, and they forget, what was that number over there? I didn't write down what that number was or how I got it. Now I don't remember, now I'm starting over. Okay, you don't want to have to do that on a test where time would be a factor. Okay, so always keep it all organized. I know it seems like a ton of work and it seems silly, okay, but there's a reason for it. Okay, and it's to help you on a question that may have many steps, okay, even something like this, to keep everything straight, okay? All right, let me clear this stuff off of here. Now, let's go back to this situation here. So that object is accelerating. You can see that its velocity is increasing. Okay? Acceleration is the rate at which velocity changes, in the same way that velocity is the rate at which position changes. Okay? So when I wanted to calculate the velocity from this graph, I went final position minus initial position, and I divided it by time. Could I do something similar to calculate the acceleration of the object? Off of that graph, can I tell what its initial and final velocities are? Okay, so could I go like this? Right? That would calculate for me the rate at which velocity changes. That's acceleration. Looks just like that other formula, which we learned yesterday is really just this formula. Right? It was the slope of the line on the position time graph. Could I say the same thing for the velocity time graph? Would the slope of that line be the acceleration? I think so, because y, b, x. It's the same thing. Okay? Slope tells you the rate at which y changes over x. On a position time graph, that's meters per second. Okay? On a velocity versus time graph, it's meters per second per second. That's the rate for acceleration. How many meters per second you change your velocity by every second. Okay? Everyone follow me so far? Don't worry, we're going to spend lots of time on this. Okay? If you're feeling a little lost, don't worry. Repetition will help. Could I calculate the displacement of that object? The diagonal line? Okay? But here's the problem. Doesn't the velocity change on that graph? Right? This is great when the velocity doesn't change. V equals d over t is fine, but now the velocity is changing. It's actually still okay. I can still use that formula because it's diagonal. It's changing evenly. Okay? So when I calculated this displacement here for this line, right? It was basically, we just went height, okay, we did the 260 times 5. Did I find the area of that rectangle when I did that? I took the height of that rectangle, 260, and I multiplied it by the base of that rectangle, 5, and I got 1,300 meters. How do you find the area of a triangle? Oh, now I'm asking you to go back to like grade 8 geometry. How do you find the area of a triangle?
Base times height divided by 2.
Base times height divided by 2. Okay, so let's have a look at that. Base, that would be time, times height over 2. Well, if I want to manipulate this, I need to go average velocity times time. Okay, so my velocity is changing. Can I get the average? Like, if this is my initial and this is my final velocity, would the average be halfway? So I could go base, that would be time, times height over 2, that would be my velocity, average. and I'd be calculating the displacement of an object that's accelerating. Okay? I don't expect you to remember this right away, okay? Again, repetition is important for stuff like this, all right? But it allows me to be able to calculate those kinds of things, okay? I'm still just using this formula. I haven't taught you anything, like, or we haven't used this one yet, but we've done everything with just that formula so far. All right. Okay, what's going on in this graph? So this is a runner, right? What's the runner doing in that part of the graph? Emma, what's it doing?
Accelerating.
It's accelerating, velocity's going up, getting faster. Okay, that's what you do at the start of a race. Okay, now what's the runner doing right there? Ollie, what's the runner doing in that part?
Running at a constant speed.
Running at a constant speed. Okay, and then what are they doing at the end? Slowing down. Do they come to a stop? Would this be zero? Line gets there, right? So they actually come to a stop at the end. They slow down, they slow to a stop. Okay, is that typically what you do in a race? It is, right? You accelerate, you know, the gun goes off, you jump out of the blocks and you're running as fast as you can. Okay, you're accelerating. Then it comes to a point where it doesn't matter how hard you push, you simply cannot run any faster, okay? And you run at that speed until you get to the finish line and then you stop. Okay, that's what any runner's graph would look like. This runner is not particularly fast. Okay, 8 meters per second sounds fast, but it's not. Okay, this is the kind of analysis, like if you're really interested in maybe getting into like sports as both an athlete or maybe as a trainer or a coach, being able to analyze graphs like this is important because it can help you find your athlete's strengths versus their weaknesses and how you can kind of tailor their strengths to maximize their performance. Okay, right now for me, I would say for this person that their rate of acceleration is pretty good. They get to their top speed pretty fast. Their top speed sucks. Okay, if there's something we need to work on with this athlete, it's they need to be faster. Okay, they're pretty powerful. They got to that top speed very fast, but they didn't have a very good top speed. Okay, if you're looking at just like something simple like the 100 meters. Okay, there's basically 2 different types of 100-meter runners. Shorter, powerful runners. Okay, they're going to be bulky, very strong looking, very thick. Okay, they're going to be very powerful. They're going to accelerate to their top speed very quickly. But because of their body type, shorter legs, bigger mass, their top speed won't be as good. Okay? Now, if you're looking at the other type of sprinter, they're the Usain Bolt type, okay? They're 6'7", they're all legs, okay? They're kind of, you know, gangly looking almost, okay? They are not going to be powerful, but when they do get up to speed, they're going to be faster than everybody, okay? It's actually why Usain Bolt was a better 200-meter runner. He was a terrible accelerator, okay? Absolutely terrible. Right? He basically could just stand up and start running. The blocks were useless to him. Okay? But once he got up to top speed, he would reel everybody in. He almost, I think I only saw one race where he led from start to finish. In almost every race he ran, including his fastest ones, okay, where he's still holding the world record. He had to catch everybody, and he does every single time. I'd hate to run in a race against that guy because you'd hear his footsteps all the time. Okay, because he would just reel everyone in. That guy could run at over 17 meters per second at his top speed. Okay, he would run the 100 meters and he would take 32 strides. Most runners take 35 to 38 strides. Okay, but he's 6'7". He gobbles up the track like you wouldn't believe. Okay, now just to give you an idea, 17 meters is from that wall across the hall and into the lab, about halfway. Okay, 1 second. Does he run that fast the whole race? No. Okay? But he only has to run that fast for about 30 meters and nobody's going to catch it. Okay? So you would analyze his graph. His graph, by comparison, would look more like this. Okay? He takes a long time to get there, but boy, once he gets there, look out, because he's really fast. Now, what part of his game would you work on? You're already stupid fast. I just need you to accelerate. I need you to be a little more powerful. Okay? You'd work on that part. Okay? So this has application in places, right? If you're a football player, like running the 40 is one of the kind of best measures of your power and acceleration. Okay? Well, you don't see too many football players built like Usain Bolt because they get their legs and arms broken all the time because they're too tall. Okay? But okay, you're going to be, you're never going to have to run more than 80 yards probably at a time, so you need to be powerful. You need to be strong and quick. Okay? So there's different, you focus on different things. Okay. So, velocity versus time graph. What's that object doing?
Stay the same.
Staying the same. Yeah, its velocity isn't changing. Okay? Because, what's the slope of that line? 0. Right? Y equals 0 times x plus 5. Okay? That object is not accelerating. We can tell that from the shape of the graph, but the slope is also 0. Okay? And the slope on this graph is the rate at which velocity changes. So it's not accelerating, it's traveling at a constant velocity. Okay? What velocity is it running at? Five meters per second. Okay? Everybody with me there? Okay? Kind of simple interpretation kind of thing. And if I wanted to calculate the displacement of this object, I know its velocity, 5 meters per second. I know it runs for 10 seconds, right? That's going to be, okay, d equals average velocity times time. That's also the height times the base. I'm finding the area of that rectangle. Okay, either way, it's positive 50 meters. Okay, making sense? All right. Did I put this graph in your notes? Remember not. I did. Okay, let's just have a look at this one here. So we've got a velocity versus time graph. Okay, here's what I want you to do. Okay, see if you can calculate for me those two things. Those don't require any skills you don't already have and have been using all week. Okay, are these still like y equals mx plus b problems? They are, okay, just like what we were doing before. Any graph that's linear like that can use y equals mx plus b. Okay, so the good news is that skill is transferable to basically any graph that you will do that's at least a straight line. Okay, so on this one here, okay, if I want to figure out how fast, this is a velocity time graph. How fast is on the y-axis. So I'm solving for a y value, so I'm just going y equals 2.96, okay, times 32 seconds plus negative 0.182. All right. So 2.96 times 32 plus negative 0.0018, right? No, 182. Okay, so after 32 seconds, this thing should be moving at 94.5 meters per second. Okay. How many people are done the second? Okay. So on the second one, how long? Time is on the x-axis, so y equals m times x plus b. Subtract b from both sides. Got y minus b equals m times x. Divide both sides by m. All right, solving for x. 90 meters per second minus negative 0.182, okay, divided by the slope, which was 2.96. Okay, so 90, we'll just say plus 0.182 because it's minus a negative, equals, and then divide by 2.96. Okay, so that'll take 30.5 seconds. Okay, on this graph, the 2.96, the slope, what does that represent? Okay, again, I'm walking you through the method I want you to use here. Okay, slope on any graph is the rate at which y changes over x. The rate at which velocity changes over time. What do we call a change in velocity? Acceleration. The slope on this graph represents the acceleration of the object. Okay, so if this is acceleration, okay, on the x-axis is time, what would b represent? B is always the initial value of y, or the value of y at time 0. What's on the y-axis? Velocity. So this would be the initial velocity. Okay, so this is VI, and that would mean that y is VF. Are all of those things in this formula? Okay. Is this formula the same as this? It absolutely is. Okay? Slope is the rate of change of velocity. That's acceleration. Y is final velocity. B is initial velocity. X is time. Okay? It's another formula that's just the slope of a line on a graph. Okay? So now we've got that V equals D over T is the slope of a line on a position time graph. This, the acceleration formula, is the slope of the line on the velocity time. Okay, so when I did this calculation right here, when I solved for y, I was really just doing this. Agreed? It's basically the algebra to solve for VF. Okay, the same is true here. This was VF minus VI over A equals T. All the manipulations of that formula that we'll eventually learn how to do. Okay, last thing we got to talk about here before we move on to doing a few of these on our own. Units for acceleration. Okay, so if I'm calculating acceleration, I'm going to have meters per second minus meters per second. So it stays meters per second. And I'm dividing that by time, which is seconds. Okay? If I divide meters per second by seconds, I get meters per second, okay? Which would be the rate at which I change my velocity, right? If I'm going faster, it would be this many meters per second faster. Okay, if I'm slowing down, it's this many meters per second slower. Does it take a long time to say meters per second? Okay. Let me show you a little trick. We don't ever say it that way in physics. Okay, we do this instead. Meters over seconds divided by seconds. Now, if I just write seconds, can I also say that that's seconds over 1? Same thing? Okay. If you want to divide fractions, what do? What do I do to the second part of this? Flip it, and then instead of dividing, I multiply. Okay, so, whoa, not what I want. Come on. Okay, so I reciprocate that and I multiply. What's meters times 1? Meters. What's seconds times seconds? Seconds squared. That's how we say meters per second. We just say meters per second squared. Faster. Okay? So the units for acceleration are meters per second squared, which is another shorter way of saying meters per second. Okay. All right. I'm going to give you guys about a 5-minute break here. Get up, walk around. Okay, take a little body break here. Okay, next thing we got to talk about with velocity versus time graphs is calculating displacement. Okay, we already kind of looked at that when we had 2 simple graphs, one that was just a triangle and one that was just a rectangle, okay, and we could just go average velocity times time, base times height, okay. But sometimes you're going to run into a graph that is either irregular or is linear like this, but doesn't make a perfect triangle. Okay, I know this one doesn't make a perfect triangle because it doesn't start at 0. So if I'm looking at this graph, would it make 2 shapes? Right, makes a triangle and a rectangle. Can I still do V equals d over t, do average velocity times time for both of those? I can, and that's what I have to do, all right? So what we would do is find the displacement, how far would the object go if it just stayed traveling at its initial velocity, okay? If it didn't accelerate, this is how far it would go. That's just going to be a matter of taking the initial velocity and multiplying it by the time, or the base times the height of the rectangle. Everybody follow me there? Where do I get that initial velocity from? Because I can't read it off the graph, but it might be somewhere on the graph. Right here. Yeah. Got to remember that the initial value of y on this graph is the initial velocity. So b is the initial velocity. So if I want to find displacement, I'm just going to go average velocity times time, 4.14 times 10. So 41.4 meters. Okay, that's how far the object would go if it didn't accelerate. But it clearly does. So I've got to figure out how far it's going to go while it's accelerating. That would be the triangle. Okay. Now, I still want to do this. I still want to say d equals average velocity times time. Okay, I still want to do that. Is the time still 10 seconds? Okay. The base of this triangle is still 10 seconds. So that part's still going to be the same. But I've got a triangle, not a rectangle. So if I want to find the height of a triangle, it's base times height over 2. Okay, now, This triangle doesn't start at 0, does it? Okay, it starts here at 4.14. How do I know where it ends? It's not something I can read off the graph, but could I calculate it? Okay, the top of this triangle is y. Agreed? Okay, so can I calculate y if I have the equation? I absolutely can. Okay, so I'm just going to do that. I'm going to calculate what y is. All right, so y is going to be 3.3 times 10 seconds plus 4.14. Okay, so the top of that triangle is 37.14 meters per second. Okay, so that means the height of the triangle is this much minus that much. Everybody okay with that? Okay, so basically it's going to be 33. Okay, well now I got the height of the triangle. If I want to find the displacement, I need base times height over 2, or average velocity. The height of that triangle divided by 2 is the average. Okay, and here's why. Here's the halfway point. For half of the time, does the object go slower than that? It does. And for half of the time, it goes faster than that. This is like having a class of 2 people. Okay? One of them gets 10 out of 10, the other gets 0 out of 10. What's the class average? 5. Okay, that's what we're doing here. We're saying here's the initial, here's the final, the average is halfway between the two. Okay, and that's perfectly fine because it's a straight line. Okay, so I'm just going to go base times height over 2. Okay, in the end, you got to be able to do this area calculation. I would really like for you to understand what you're doing when you do the area calculation. That's important going forward in physics. But you could get by if you just remember base times height over 2 and then promise you don't take physics. You got to understand why we're doing it. I'm just kidding. It's just an area calculation. Okay? All right, so I'm going to go base. That's 10 times the height over 2. Okay? 33 over 2 is 16.5. Okay, so while accelerating, it goes 165 meters plus the 41.4. So we should be looking at 206.4 meters, I think, okay, in total. So area of this plus area of that. If you're looking for a little rule or trick, okay? Displacement on a velocity versus time graph is always the area between the line and the x-axis. And you can always make that area triangles and rectangles. So as long as you can remember, okay, how to calculate the area of a rectangle and the area of a triangle, you can always calculate the displacement of an object from its velocity versus time graph. Okay, that's a little trick. Okay, what's that object doing? Slowing down, okay? Which is still an acceleration, right? Because acceleration is any change in velocity. This time the acceleration is negative, okay? And it does eventually come to a stop according to the line. Okay? Calculate for me, using the equation, at what time it stops. According to the line, not according to the point. Okay? According to the line, when does this object stop? Just push the button to open up. That's the key. Okay, so if we're trying to figure out at what time this object stops, okay, I'm giving you the y value, and it's what? What is y when the object is stopped? 0. Okay, so I'm telling you y equals 0, and you're looking for x. Okay, so we've got y equals m times x plus b. Right? It's wording that can be tricky. If I had just said what x value is y0, you just set this up right away. Okay? But as soon as I put it in a context, like when does it stop, and I don't actually tell you any numbers, it's trickier. Okay? So I'm looking for x, so x will be y minus b over m. That's going to be 0 minus 27.5 divided by negative 3.02. Right? On the top, I'm going to have meters per second, and on the bottom, I've got meters per second squared, because that's the acceleration. Okay? So the meters will cancel, and one of the seconds will cancel, and I'll be left with seconds, which is what I'm looking for. Okay? So negative 27.5 is the top, well, 0.5. Okay? Divided by the bottom, negative 3.02. All right, so that should take 9.1 seconds. That looks like about where the line crosses the x-axis, okay, at around 9 seconds. Okay, everybody okay with that? So that's just a y equals mx plus b calculation. All right, now I want you to calculate for me the displacement of this object. Now we know the time. Once it stops, we're done. Okay, so we're looking at the triangle that is formed by that line of best fit. Okay, calculate for me the displacement. Okay, so displacement is average velocity times time. Okay, because this is an object whose speed is changing, the average velocity will be halfway between the initial and final velocities. The height divided by 2. Okay, it starts at 27.5, okay, because I get that from here, and it ends at 0, because I can see the line gets to 0. Okay, so the average speed is halfway in between. Right, so I can just then go base, that's time, times height over 2, that's average velocity. So the base is 9.1 seconds, that's why I had you calculate it. Okay, and then times the height over 2, 27.5 over 2. Okay, so it's going to travel 125.125 meters. Okay. Everybody okay with that? All right, so just talking about velocity versus time graphs in general, okay, the things we can read directly off the graph: instantaneous velocity, or velocity at a time, okay, and obviously we can read the time, okay, velocity, we can read time. We can tell what kind of motion is going on. It's either traveling at a constant velocity or it's accelerating, okay, it's a diagonal line, then it's accelerating, okay, and then of course, the area under the line on a velocity versus time graph. Actually, it shouldn't say under the line, okay? It should say between the line and the x-axis. Okay, and the reason I say that is because if you have a graph where the x-axis is in the middle and your graph goes like this, you don't want to calculate the area under the line. You want it between the line and the x-axis. Okay? That is going to be the displacement of the object. Okay? So that's an important one to remember. Okay, the other thing. Okay, anybody need that anymore? All right, we did the position versus time one. Okay, so this is question, I think it's question 4, on your, yeah. Okay, so this is question 4 on your workbook here, okay, that we were working on yesterday. Okay. Just because these graphs are irregular doesn't make the rules we just learned on a linear graph wrong. Okay, they are still true. Okay, these formulas, which are on your formula sheet, still apply. Okay. So if I want to calculate the acceleration between 12 and 14 seconds, so for part A, okay, I need to get from the graph the initial velocity, the initial velocity, the final velocity, and the time. Okay, it's a velocity time graph, so I can get those things. So 12 and 14 seconds. Okay, so there's 14 seconds. VF is going to be -6 meters per second. Okay, VI happens at 12 seconds. That's right here. It's +2 meters per second. And obviously the time between 12 and 14 seconds is 2 seconds. Do I have enough to calculate the acceleration with that formula? Okay, then just plug in the numbers. Okay, so that'll be -6 minus 2 divided by 2. Okay, so -8 divided by 2 is -4 meters per second squared. Okay, so we will be using that formula a little bit. You won't have to manipulate it when we're doing graphs. You just have to use it. Okay, just like you did final position minus initial position over time. It works exactly the same. Okay, now for part B. If we're going to find displacement, that's all the shape stuff that we just learned. Okay, so between 0 and 20 seconds. So that's the whole trip. Okay. What is the object doing right here for the first 2 seconds? What's its velocity? 0. So for the first 2 seconds, the object is not moving. That means it doesn't have any displacement in the first 2 seconds. Would you agree? Okay, and there's no shape there, right? It's on the x-axis. There's no area between the line and the x-axis for that part. Okay, then it drops down here. It accelerates, it accelerates, it accelerates differently, travels at a constant velocity for a while, accelerates, accelerates, travels at a constant velocity, accelerates. Okay, are there a lot of shapes? Okay, all your triangles, make them right angle triangles. Okay, so just start drawing pictures of triangles. Okay, and rectangles. Okay, have I accounted for all the area between the line and the x-axis? Right? I've included, everything is included in some rectangle or triangle. Calculate all their areas. Now, okay, calculate all the areas of those triangles. Base times height over 2, or for the rectangles, because there's 2 rectangles in there, base times height. Okay, it might be easier to read it off of your graph. There is this one here, I will warn you, this one here is half a second, okay, on the base, right, because it cuts one of these blocks in half. So it's half a second here and half a second there. Just be aware of that. Give you some time to do your geometry review here. Just so you know, on a unit exam, I would never give you one with this many shapes. This is just to help you review your geometry a little bit. At all of these shapes here. All right, so obviously there's no shape here in the first part because it doesn't move for the first 2 seconds. And then, okay, we've got this triangle here that goes -3 down, so below the x-axis, and is 3 seconds on the base. So -3 times 3 is -9. It's a triangle, divide by 2, you got -4.5. Okay, then we've got this triangle here that has a height of -3 and a base of 1. -3 times 1 is -3. Divide by 2, you got -1.5 meters, okay, as the displacement in that one. All right, then we've got this one here that has a height of +2 and a base of 1. 2 times 1 is 2. Divided by 2, this is +1. All right, this one here is 5 seconds long and 2 high. 2 times 5 is 10 because it's a rectangle. Okay, this one here is really small. It's 2 high by 0.5 on the base. 2 times 0.5 is 1, divided by 2 is 0.5 meters. That's also positive. Okay, then we've got this triangle. It is 6 deep, okay, or high, -6 high, okay, and 1.5 on the base. 6 times negative, or -6, sorry, times 1.5 is -9. It's a triangle divided by 2. You got -4.5 meters. Then we have this triangle here that goes from -2 to -6. So it has a height of 4, a base of 2. 4 times 2 is 8, divided by 2, okay, is -4 meters. We've got this triangle here, or this rectangle, sorry, that's -2 high by 4 long, right? So that'll be -8 meters. And then we have this triangle here that's -2 high on 1 on the base. -2 times 1 is -2. Divide by 2, you got -1 meters. Okay, so that's all the areas on that graph. Okay, how do I get the total displacement? Add them all up, but make sure I keep I gotta keep the negatives. Okay, I can't just add them, add the numbers. I have to add with the negatives in there because this thing goes backwards more than it goes forwards, right? We spend more time below the x-axis going backwards than we do above the x-axis going forwards. Okay, so we add those numbers together, yes, we do that, but we have to keep in mind that some of them are backwards. Right, so we'll have -4.5 plus -1.5 plus 1 plus 10 plus 0.5 plus -4.5 plus -4 plus -8 plus -1. Okay, so in doing all of this, we end up 12 meters behind where we started. Okay, our total displacement here is -12 meters. All right, part C wants to know the average velocity, I believe, right? Okay, have you done all the heavy lifting to do that? Okay, average velocity, guys, just because this is a velocity versus time graph does not mean that average velocity is not still total displacement divided by total time. You just did all the work to get the total displacement. The total time you can read off the graph, it's 20 seconds. All right, so all we have to do, okay, is take our -12 meters divided by 20 seconds. That's -0.6 meters per second as an average velocity. Okay, for D, average acceleration. Can I use that formula for D? Okay, because it says between 14, that's here, and 20 seconds, that's here. Okay, pretty sure I can read initial and final velocities off of the graph, and I'm pretty sure there's 6 seconds between 14 and 20 seconds. Okay, just plug the numbers into the formula. The final velocity is 0. Okay, the initial velocity at 14 seconds is -6. 0 minus -6 is +6, divided by 6 seconds, and you've got +1 meter per second, or meter per second squared. Okay, do part E. Okay, average speed to 20 seconds. Once again, you have done most of the heavy lifting for that. Just one little thing you need to change. Okay, is average speed still total distance divided by total time? Okay, so what do I do different than what I did in part C? In part C, the positive and negative mattered. Does it matter now? Okay, so to get total distance, I simply add all those numbers together. Okay, so 4.5 plus 1.5 plus 1 plus 10 plus 0.5 plus 4.5 plus 4 plus 8 plus 1. Okay, did I do that right? 35? Okay. So 35 meters is my total distance. Okay, total time, 20 seconds. V equals D over T, 35 over 20, okay? Should give us 1.75 meters per second. Okay? So lots of applications of all the stuff we've been doing over the last little while, and that's what you're gonna find. It doesn't matter what graph we're dealing with, there's really about 3 or 4 formulas that apply. Okay? All right, tomorrow you have a quiz. Velocity versus time graphs, everything we did today is not on that quiz. Okay, what will be on that quiz will be 2 of the multi-part V equals D over T questions and 1 position versus time graph. Okay, I don't even think it'll take us the whole period, okay, but we'll have it if we need it. Okay, so be ready for that. Practice quizzes are here, guys. Okay, I think on 5 and 6 there might be velocity versus time graph questions on those. Just don't do them. Just focus on the position versus time stuff. Okay?